The blazing sun beats down mercilessly on the ancient city of Mohenjo-daro as temperatures soar past 120 degrees Fahrenheit. The air shimmers with heat waves that would overwhelm modern air conditioning systems. Streets that should be abandoned lie empty under the crushing weight of summer's fury. Yet archaeological evidence reveals something extraordinary. These ancient settlements didn't just survive these extreme temperatures. They thrived in conditions that would send modern city dwellers fleeing to climate-controlled refuges. How did civilizations spanning from Mesopotamia to the Indus Valley create urban environments that remained habitable during heat waves that would cripple contemporary cities? The answer will completely revolutionize what you think you know about ancient engineering and urban planning. Excavations from dozens of major archaeological sites across the world's hottest regions reveal a shocking truth. Ancient cities weren't primitive settlements struggling against the heat. They were sophisticated thermal engineering marvels designed specifically to combat extreme temperatures without any mechanical cooling systems whatsoever. This wasn't accidental survival. It was calculated urban design that prioritized thermal comfort through revolutionary architectural principles. Using strategies so effective, they enabled the rise of massive civilizations in deserts and heat-scorched plains where modern cities would be uninhabitable without constant artificial cooling. The story begins with a fundamental misunderstanding that modern urban planning gets completely wrong. Fighting heat with brute force mechanical cooling creates more problems than it solves. When you're designing cities in regions where summer temperatures regularly exceed human survivability limits, every building, every street, every public space becomes a potential death trap without proper thermal management. But how do we know ancient cities actually succeeded in beating extreme heat? The answer comes from the cities themselves, preserved for thousands of years beneath sea layers of sediment waiting to reveal their thermal secrets. The most compelling evidence emerges from Harappa and Mohenjo-daro in the Indus Valley, where summer temperatures reached 125 degrees Fahrenheit. These cities, dating from 2600 to 1900 BCE, were exhaustively excavated by teams from the Archaeological Survey of India and international research institutions. Archaeologists recovered drainage systems, residential complexes, public baths, and even preserved organic materials from ancient cooling systems. But here's what made researchers completely reconsider their understanding of ancient urban planning. Across both cities, representing different construction phases and social districts, not a single building showed evidence of the heat-related structural damage that plagues modern desert cities. No cracked foundations from thermal expansion, no evidence of heat-warped construction materials, nothing. This thermal stability continues at every major ancient desert city discovery. Babylon in Mesopotamia contained elaborate palace complexes that remained structurally sound through summers that reached 120 degrees Fahrenheit. The ancient city of Mari featured massive public buildings with no signs of heat-related deterioration. Even recent excavations at Tel Es-Sawan using ground-penetrating radar and thermal imaging found construction techniques specifically designed for extreme heat management. The archaeological record confirms this pattern. Cuneiform tablets from ancient Babylon preserved in the British Museum collections describe daily urban activities continuing throughout summer months when temperatures soared beyond modern comfort zones. The Epic of Gilgamesh references bustling markets and public gatherings during seasons when the sun's heat was described as merciless and unforgiving. So ancient cities definitely succeeded in managing extreme heat. But why choose sophisticated thermal engineering rather than simply relocating to cooler climates during summer months? The answer lies in the terrifying reality of abandoning established urban centers. Ancient cities represented massive investments in infrastructure, agriculture, and trade networks. Seasonal abandonment would mean losing control of vital water sources, leaving valuable stored goods vulnerable to raiders and disrupting commercial relationships that took generations to establish. Archaeological evidence from sites across Mesopotamia shows that cities which attempted seasonal evacuation strategies inevitably collapsed within a few generations. But the real breakthrough came when ancient engineers realized that heat, like any natural force, could be redirected and controlled rather than simply endured. Urban planning excavations reveal construction principles that treated thermal management as the foundation of all city design, not an afterthought. Ancient cities used what archaeologists now call passive thermal architecture. Every building orientation, every street width, every public space placement was calculated to minimize heat absorption while maximizing cooling airflow. Physical remains from major excavations show sophisticated understanding of thermal dynamics that wouldn't be formally recognized by modern science until the 20th century. For ancient urban planners, extreme heat wasn't an enemy to defeat. It was a force to be channeled and controlled through intelligent design. If ancient cities couldn't rely on mechanical cooling systems trapped in urban heat islands during months of extreme temperatures, how did they possibly maintain livable conditions? The answer required reimagining urban design itself. Archaeological evidence from sites like Çatalhöyük in Turkey reveals sophisticated building orientation systems that could reduce interior temperatures by 20 to 30 degrees compared to outside air. Buildings were positioned to take advantage of prevailing wind patterns, with doorways and windows placed to create natural ventilation corridors that drew hot air up and out while pulling cooler air from shaded areas. The most remarkable discovery comes from preserved architectural plans and measurement systems found at Mesopotamian sites. Ancient builders practiced what researchers call calculated solar shading. According to inscriptions found at Ur and Babylon, architects would use bronze measuring devices and shadow calculations to position buildings so that walls and roofs provided maximum shade during the hottest parts of the day. Not random placement, not trial and error construction. Mathematically precise positioning based on detailed understanding of solar movement patterns throughout the year. This daily shadow management was part of revolutionary urban planning technology. Mesopotamian city layouts show specialized cooling districts where public buildings were arranged to create what researchers call thermal refuges. These areas featured concentrated shade structures, water features, and airflow channels that could maintain temperatures 15 to 25 degrees cooler than surrounding areas during peak summer heat. The cooling system was sophisticated beyond anything attempted in modern urban planning. Each district worked together to create what archaeologists call a managed microclimate across the entire city. But even this advanced architectural planning couldn't eliminate heat during the scorching afternoon hours when temperatures peaked above tolerance levels human. That's when ancient cities deployed their most ingenious innovation. Forget Hollywood's image of ancient people cowering indoors during extreme heat. The reality was far more sophisticated and socially coordinated. Ancient cities used community-wide thermal management systems documented in multiple sources, from legal codes to religious texts. The Code of Hammurabi describes shared cooling arrangements using what Babylonian texts call community shade halls, large public structures designed not for individual comfort but for collective survival during heat emergencies. These were multi-family cooling spaces built with specialized ventilation systems where entire neighborhoods could gather during the most dangerous temperature peaks. Multiple families in climate-controlled public spaces could survive heat that would kill individuals in private residences. The halls maintained internal temperatures within human survivability ranges using only architectural design and community coordination. Archaeological surveys of ancient cooling halls demonstrate these weren't luxury amenities, but standard urban infrastructure. Cities were required by law to maintain public thermal refuges accessible to all residents regardless of social status, as documented in legal texts from across the ancient Near East. When summer heat reached lethal intensity, entire communities would relocate to these shared spaces following rotation schedules that ensured everyone had access to life-saving cooling during the most dangerous hours of extreme temperature days. The cooling arrangements themselves showed thermal genius that anticipated modern urban heat island research by thousands of years. City planners understood that concentrated human activity generated additional heat, so cooling halls were positioned in locations that took advantage of natural airflow patterns while avoiding areas where urban development created heat traps. Even wealthy merchants and royal families participated in these communal cooling systems. Ancient cities provided no special thermal privileges based on social status during heat emergencies. Survival requirements overrode social distinctions when temperatures threatened human life, but maintaining human comfort in such extreme conditions required enormous amounts of water. For cooling systems that had to function without any mechanical pumps or refrigeration technology. Ancient cities consumed water for cooling at scales that would stagger modern urban engineers. Archaeological evidence from Babylon reveals distribution systems that moved thousands of gallons daily through networks of channels, cisterns, and specialized cooling installations that operated entirely through gravity flow and human coordination. Sites across Mesopotamia show evidence of massive water infrastructure designed specifically for thermal management. Excavations at Mari uncovered underground channels that distributed water to every major building complex, creating what researchers call hydraulic cooling networks that functioned without any mechanical assistance whatsoever. The water systems weren't simple irrigation expanded for urban use. These were purpose-built thermal management installations, documented through preserved engineering texts and physical archaeological remains. Water collection for urban cooling required sophisticated resource management strategies found in cuneiform administrative records from across the ancient Near East. Cities maintained specialized water reserves exclusively for cooling purposes, separate from drinking water supplies and agricultural irrigation systems. The scale of these operations only became clear with modern excavations using advanced surveying techniques. Research at Harappa by international archaeological teams from 2015 to 2019 revealed what these water systems actually accomplished. A thermal management network spanning 150 hectares with proper distribution channels, specialized cooling pools and residential water features that supported entire urban populations through months of extreme heat without any mechanical cooling assistance. These installations demonstrate complex understanding of evaporative cooling principles that wouldn't be formally studied by modern science until centuries later. Ancient engineers intuitively grasped that moving water across hot surfaces could reduce air temperatures through evaporation, creating localized cooling effects that made urban spaces habitable. But the real innovation came through building materials specifically chosen for their thermal properties rather than just structural strength or aesthetic appeal. Ancient cities employed revolutionary construction materials that modern thermal engineering is only beginning to understand. Analysis of preserved building elements from sites across the ancient world reveals material compositions designed to absorb, reflect, and dissipate heat through carefully calculated thermal mass principles. Mesopotamian builders developed specialized mud brick compositions that incorporated organic additives for enhanced thermal performance. Chemical analysis of these ancient building materials shows precise mixtures of clay, straw, and other organic compounds that created superior insulation properties compared to simple mud construction. The organic additives weren't random. Preserved construction manuals written on clay tablets describe specific recipes for different thermal applications, with distinct formulations for walls exposed to direct sunlight versus those in permanently shaded areas. These materials maintained interior temperatures significantly below exterior heat levels, without requiring any additional cooling systems. The buildings themselves functioned as passive thermal management devices through intelligent material engineering. Ancient architects also utilized specialized surface treatments that reflected solar radiation rather than absorbing it. Excavations across multiple sites reveal evidence of reflective coatings applied to building exteriors, created from locally available materials processed to maximize solar reflection. White lime washes, polished stone surfaces, and specialized ceramic tiles all served thermal management functions beyond simple decoration. These surface treatments could reduce building heat absorption by substantial percentages, keeping interior spaces cooler through pure material science applications. The most sophisticated thermal materials came from advanced ceramic technologies developed specifically for extreme heat management. Archaeological evidence shows that ancient potters created specialized building ceramics with thermal properties that exceeded many modern construction materials. These weren't decorative ceramics, but engineered building components designed to move heat away from occupied spaces through convection and radiation principles that ancient builders understood empirically through generations of practical experience. Underground construction provided another crucial element in ancient urban thermal management. Cities across hot climates developed extensive subterranean districts that took advantage of Earth's natural cooling properties for residential and commercial activities during extreme heat periods. Excavations reveal that these underground spaces weren't crude cellars, but properly engineered subterranean districts with sophisticated ventilation systems that maintained comfortable temperatures year-round. The underground construction connected to surface buildings through carefully designed airflow channels that created natural air conditioning through temperature differentials. Çatalhöyük excavations show underground residential areas that remained 30 to 40 degrees cooler than surface temperatures during summer months. These spaces featured proper lighting systems using reflective surfaces and ventilation networks that provided fresh air circulation without compromising thermal efficiency. The engineering required to maintain air quality in underground spaces while preserving cooling benefits demonstrates advanced understanding of air movement principles and environmental control systems. Ancient cities conquered temperatures exceeding 120 degrees Fahrenheit. Not through brute force mechanical systems, but through sophisticated thermal engineering that modern urban planners are only beginning to understand. They transformed deadly heat into manageable environmental conditions through calculated architecture, community cooperation, and materials science that prioritized survival over individual comfort. When summer heat overwhelms your air conditioning, remember that entire civilizations once thrived in conditions that would challenge our most advanced cooling technologies, proving that intelligent design can triumph over the harshest environmental extremes through human ingenuity and strategic planning.